All right, I'm now going to begin discussing descriptive statistics. I'm going to do this in several different installments. The first aspect of descriptive statistics, which, if you remember from the previous lecture on Introduction to Statistics, has to do with summarizing in order to describe your data. One strategy will be to use a visualization. Visuals are great tools that give a really impactful graphical representation of data to your audience. Everybody loves pictures, and so using pictures to describe your data is a fantastic tool for communicating about your analyses. If we're talking about describing and visualizing data, one facet of data visualization is going to be to describe distributions of scores. The basic idea is that when you collect data, you end up with a large number of what we call raw scores or raw data. Imagine, if you will, that you're surveying participants by asking them a series of questions about, let's say, their self-esteem, and you poll maybe just 20 participants. Even if you're polling that very small group of people, that's 20 people who are giving you numerical values for all of those questions that you're asking. So even really short surveys with small sample sizes yield really overwhelming amounts of raw data. So the idea is that you need to transform your raw data into something that characterizes or summarizes it in a way that actually transmit an effective message or communication about what's going on with your data. So the raw data sets themselves are typically not very informative. It's how you can transform them to characterize the distribution of scores in your data set. So take, for example, a researcher who polls 20 people on just a single question about how much sleep they received the previous night. Their raw data would look something like this, right? It's just a set of 20 numbers. Even just 20 participants giving you a single answer yields data that isn't very pleasant to look at. This is not very effective at transmitting or communicating something about the nature or characteristic of your data. So we would want to transform this into something that communicates more effectively and more clearly. One option, if you have data that looks like this, would be to create what's called a frequency distribution. So this is going to be a data visualization that shows the number of times each unique score appeared within a data set. Essentially, how many people said they slept 5 hours, 6 hours, 7 hours, etc. So it's really easy to put together a frequency distribution. You just have to figure out how many scores appeared at least once. So each unique score is what we call that. That's any score that appears at least once. Then you just count up how often each one of those unique scores appeared. You would just tally it off. And so what you're doing is you're transforming your data such that it went from this to this, right? 5 appeared in the data set at least once, 6 appeared, 7, 8, so on and so forth. Then the right-hand column is the frequency column that tallies up how often each of those scores appeared. So this does synthesize or pare down the data somewhat. As opposed to looking at all 20 of those scores, you have a stronger sense of which scores appeared the most frequently. You get a sense that most students slept in the normal range of 6 to 8 hours, with some isolated outliers further away from that more normal sleep average. So it didn't do a ton to synthesize our data down, but it was already a very simple data set to begin with. This is going to work well when you have relatively few unique scores. If you have a variable that has many unique scores that appears in your data set, a frequency distribution is not going to do very much. Let's say I put together the exam scores in a stats class for a typical semester that had 42 students enrolled. Your data set would look like this, right? You have 42 different responses in your raw data set. You can still transform it into a frequency distribution, but it just doesn't really work great. It doesn't synthesize your data down very much or at all. There's lots of scores that appear once or twice. Overall, this frequency distribution was not even really worth making because it doesn't transmit or communicate any more effectively than the raw data does. We want to come up with a strategy that really can synthesize this data down into something that does communicate something clear to your audience. So in this case, the frequency distribution doesn't really win any effectiveness points much more than the raw data did. So what you can do is, if you have a data set that has multiple similar scores or many scores that appeared the same amount of times, what you can do is you can create a grouped frequency distribution where you group similar scores together into intervals, and your frequencies are then going to tally up how many scores appeared in the various intervals that you've constructed. So frequency, a grouped frequency distribution, on the other hand, you'll see that the leftist column is going to have not just single unique scores, it's going to be intervals of scores. A couple things to keep in mind. A grouped frequency distribution, you'll notice that those intervals, they don't overlap. You'll see that this grouped frequency distribution depicts data on pulse per minute. You'll see that the interval at the top is 60 to 64. You'll notice that the next one jumps from 65 to 69. That ensures that there's no overlap between the intervals, meaning that for any score that falls on that boundary, it cleanly falls into one interval or the other. If the intervals had gone from 60 to 65 and 65 to 70, it would make it unclear as to where a score of 65 would end up. So those intervals don't overlap, ensuring that all of the raw data points make it into one interval or the other. Additionally, all those intervals are the same size, regardless of how many scores fall into that interval, or even if an interval had 0 scores in it. The idea is that you want to have all of these intervals be the same space, and you want there to be intervals for all of the numerical space in between the lowest boundary of the lowest interval, the 60 here, and this 99 up here. You need even intervals that transcend all of that numerical space from this lowest bound to this highest bound here. Once the intervals are created, the steps for finishing the grouped frequency distribution are the same. You just tally up how many scores appeared in these various intervals. Again, the idea is that this transforms data that might have theoretically many unique scores that all appeared the same amount of times, and it still synthesizes it down further such that it still helps communicate clearly about your data. So if you were to do the same thing to that exam data that I showed you a couple slides ago, it would instead look like this. So as opposed to the regular frequency distribution that really didn't do much to synthesize the data down, this actually does give you a better handle on describing what's going on with your data. You can see that most of the scores are clustered around the 80 to high A kind of a range. So this actually did take that raw data set of 42 scores and transform it into something that clearly communicates and describes something about your data. So this would work a lot better than a regular frequency distribution for data that looks like this. Another approach for visualizing your frequency distribution based data is to create what we call a cumulative frequency distribution. So this is basically going to be when you have your column with the frequencies, whereby as you ascend up numerically through the intervals, the value listed in the frequency column is the sum of all of the scores beneath it. Essentially, what this would be tacking a new column onto the frequency distribution where you create what's called a cumulative value. Cumulative means the sum of, so the value as you ascend up through that cumulative frequency column is going to be the sum of that value and all the values beneath it. What this does, it essentially allows you to figure out how many scores fall beneath certain thresholds in your data. So how many people fell below a certain percentage? How many people had a score below a certain threshold? This is helpful for when you want to visualize what we call percentiles. This is essentially any time you want to identify a score that has a certain percentage of people below it. So for example, if you took the ACT and you were in the 90th percentile, that would mean you performed better than 90% of the people. It's just a different way to visualize data that looks like this. You can additionally take your frequency distribution and you can transform it into something that uses lines or bars. You can essentially turn it into an even more impactful visualization by taking those numerical frequencies and turning it into something that's even more visually appealing. And you can do the same thing with your cumulative frequency. For example, this graphic on the right depicts a cumulative frequency depiction of snow accumulation. So if it's a variable that you might be interested in looking at cumulative levels, then this sort of a depiction might work really well for communicating that information, right? Something like snow day to day over the winter season is maybe not going to be as informative as knowing just how much snow there's been cumulatively throughout the winter season. So it's all about thinking about what's the most effective way to visualize your data. So if you were to just take that grouped frequency distribution from that exam data I showed you and create a cumulative frequency column, right? The idea is that you would go from the bottom to the top, or you would start at the lowest value, all the way up to the highest value, and essentially you would create a new value in the cumulative frequency column, where as you ascend, the value in the row is the sum of the value from that frequency row and all of those beneath it, right? So this bottom score here is a 1 because there was only one value that fell into 42 to 47. There were 0 scores in 48 to 53, so on and so forth until you got to the 66 to 71 interval, where there were 3 scores in that interval. The value that gets entered into the cumulative frequency is 4, because that is the sum of that 3 in the 66 to 71 interval and the 1 down there in the 42 to 47. Then when you're moving up to this row representing the 72 to 77 interval, you take that 4 from right beneath it and you add it to the 4 from the frequency for that interval. So on and so forth until you get to the top. You can verify that this is the correct value because it should add up to the total number of scores in your data set, or your N. Again, these are just different options for depicting the data. Again, it depends on what your goal is and what you want to communicate about your data. Here are some more examples of some group frequency distributions. I showed you this pulse per minute one. Again, the idea is if you want to create a grouped frequency distribution because you have many unique scores, the group frequency distribution is likely going to be a good option for you. You can use a frequency distribution to depict categorical data. If you have categorical data, right, again, recall that a categorical variable just indicates category or group membership. So let's say you have a categorical variable like asking people to identify their major. This is a categorical variable, but you can still count up the frequency for how many people fell into that group. So you can take that categorical data and you can depict the frequencies, and that's just, again, a way to describe something about what's going on with your major variable. You can eyeball the frequency distribution and say, oh look, the vast majority of people in this group are psychology majors. You could create a frequency distribution for people's responses on a Likert scale or any sort of quantitative response self-report scale. So how many people who are responding a scale on their rating for any course that they're taking from bad to very good. You can depict that frequency data. You can turn it into a percentage-based data by taking the frequency and dividing it by 100. And you can create a cumulative frequency, and you can even create a cumulative percentage. These are all just different options for communicating and synthesizing down and visualizing your data. And now just a few more options that you have in terms of visualizing your data. One is going to be a histogram. So this is related to a frequency distribution in that a histogram is simply a visual representation of a frequency distribution wherein the frequencies are depicted as bars. So you just use a bar chart and the height of the bars indicate how many people fell within whatever interval is depicted along the x-axis. So again, a histogram, it's just a specific kind of bar chart that depicts frequencies. Not all bar charts are histograms, but all histograms are bar charts. Again, a histogram is a bar chart where the data specifically is depicting frequencies. A frequency polygon is exactly like a histogram except for aesthetics. A frequency polygon is a histogram, but instead of bars, there's a single continuous line. A frequency polygon is just an example of a line chart, but it's specifically a line chart that depicts frequency-based data. So the difference between a histogram and a frequency polygon, it's entirely aesthetic. It's depicting the exact same kind of information. So at a certain level, decisions about what kind of graphic to use can come down to aesthetic preference. There's various sort of tips and tricks and sort of like commonly held best ideal circumstances for using a given visual that I'll get into, but at a certain point, you can decide what you think looks the best. As long as a graphic is accurate in depicting the data, it's not necessarily a wrong choice. Again, there's certain sort of generally held notions about when different graphics are more appropriate or more effective, but if you like the look of a frequency polygon better than a histogram, that would be entirely your choice because they represent the exact same kind of data. If you wanted to go real quick from, sketching yourself a histogram to turning it into a frequency polygon, all you would have to do is draw a dot at the top of each bar and then connect the dots with a single continuous line. Again, the difference is merely aesthetic. And then before I show you the last kinds of graphics you might encounter, I want to show you how you would create your frequency distribution in SPSS. So here are some screenshots depicting that exact exam data in SPSS. One thing to note is that SPSS data input is always done row by row, indicating participant by participant level. So you would need to have a separate row in SPSS for all 42 of your participants. So that's what the data is doing here. If you were to go to the chart builder and select histogram and then select that you wanted the exam 1 variable to be depicted in the histogram, this is what SPSS would spit out at you. So you'll notice that it is a grouped frequency histogram. SPSS sort of has its own algorithm for how it decided to group together similar intervals. Again, it comes down to how best you can communicate something about the data. Again, the major point is that various graphics and decisions about how to visualize your data might all be equally correct. It's just about deciding how you can most effectively communicate and describe something about the characteristics of your data. So then, finally, a few more options of graphics to use. You've got your bar charts and or referred to as column charts. So as alluded to when I spoke about the histograms, bar charts are just going to be data it's going to be a visualization where data points are depicted as bars. So bar graphs are thought to be particularly good for comparing frequencies between different categories. Again, it wouldn't necessarily be right or wrong to use a line chart to depict frequencies. It's just the sort of general idea or general rule of thumb that if you have frequency-based data, a bar chart wouldn't be a bad idea. So the basic way that a bar chart works is that you've got the categories depicted along one axis and the numerical scale depicted along the other axis. You can see here this graphic depicts Olympic medals of all time, gold, silver, bronze, in different countries. So a few things to note about this particular graphic. This demonstrates that, again, there's aesthetic preferences that you can employ in deciding how to visualize your graphic. You'll notice that this bar chart appears to sort of be flipped on its side, as opposed to being up and down. That's perfectly fine for the bars to be going horizontally or vertically. It's completely up to you. It would be perfectly accurate to flip this data back up such that the country categories were on the bottom and the numerical scale was going upwards. Sometimes it just comes down to what sort of space you have on the page that you're writing. So again, completely up to you. You can change things around with your graphic, like the orientation, just fine. Another thing to note is the legend indicating that the different colored bars indicate different categories, right? So it's got the country information, it's got the number of medals, that quantitative axis, and then it breaks things down further by gold, silver, and bronze. So you can visualize slightly more advanced information, like the different categories of medals in different countries. The idea is as long as you have a clearly labeled axis indicating what the different colorful bars mean, then it's visually impactful and it's clearly communicated to your audience. So choosing something as simple as choosing a really good effective color scheme, a legend that indicates what the different colorful bars mean, that's a great way to A, make your visualization more impactful, and just make it more aesthetic. It's just fun to look at. Why not? Additionally, it's important to note that not all bar charts are depicting frequencies. A bar chart is any chart whereby the data is visualized by a series of bars. But there's data that exists that can be depicted by bars besides just frequencies. You might be depicting means, for example. So that's what this graphic depicts. This graphic depicts, for example, data broken down in men versus women, And what it appears to be depicting are data that is just averaged together. So this is not depicting number of frequencies. As the title says, it's mean totals by various sections by gender, broken down into sections 1, 2, 3. And then the color legend indicates which bar represents women and which one represents men. Again, this would be an example of a bar chart, but it's not a histogram because it's not depicting frequency-based data. Perfectly valid use of a bar chart. Again, it's all about making sure that your graphic is clearly labeled and sort of as concise and clearly communicated as possible. A line chart, on the other hand, is going to be any visualization in which the data is depicted by a solid continuous line. So again, it's not to say that there are hard and fast rules about when you should use a line chart or a bar chart. There's just general rules of thumb. So typically we think of line charts as being particularly effective for depicting change across time. Again, this is not a hard and fast rule. You can at a certain point choose whichever graphic you think looks the best while still accurately depicting your data. But in general, if you do have change across time based data, typically we would think a line chart is a good idea for that visualization. So in my mind, I always think of this rule of thumb as being because the continuous line sort of evokes the continuous nature of time. So the fact that there's a continuous line representing that there was time elapsing in the interim between these data points, that's just sort of how I always think about why this is the rule of thumb. But again, it would be valid to visualize data like this using a bar chart. But as you can see, this visual here depicts data across different sales seasons. I don't know. I don't understand anything about business. But basically, if you're depicting data month by month, a line chart might not be a bad idea. It doesn't have to be such long spans of time, like months or years. It could even be across minutes or hours. And again, as long as you have clearly labeled axes and legends, then you can sort of play up your graphics and you can depict slightly more complicated information in really effective ways. So for example, this data depicts change in heart rate across spans of 15 minutes in participants that either were exposed to a violent or nonviolent stimulus. And the idea is that you can chart changes to heart rate across time. This is something that we sort of conceptualize as changing across time. Again, you can have your across time data depicted as being broken down by groups as long as you have some really clear labeling going on. That's a really key thing to take away from learning about graphics and visualizations, is it's about communicating as clearly and as concisely as you possibly can. Here's another example of a line chart to again depict that it's not a hard and fast rule. You can have a line chart that does not depict change across time. So for example, this graphic indicates social media participation in men versus women. This graphic doesn't indicate what the dependent variable is, that label along the y-axis, but still, as you can see, this data appears to be breaking down levels for some outcome between men and women, and the different lines indicate people that either participated in or did not participate in social media. So personally, I look at this graphic and I think to myself, it likely would have been more effective to use a bar chart. I think the solid continuous lines are a little bit confusing. Why not just have a bar indicating men who were in social media and men who weren't, and likewise for women? I think that this sort of demonstrates that it's most important to be accurate, right? As long as this data is accurately depicted, it's fine. But you can ask yourself whether or not this is really the right choice. Is the line chart really communicating as clearly and effectively as possible? Would a bar chart be a wiser choice? Then lastly, everybody's favorite, who doesn't love a pie chart? Again, a rule of thumb for when to choose a pie chart is typically when you're trying to show data broken down proportionally, so depicting all of your categorical outcomes as pieces of the whole. So how much of the pie did any given category take up from the 100% whole of the pie? So if you're trying to show proportional breakdowns, a pie chart might be a good choice for you. So in particular, if you're trying to divide categorical data in terms of how many people lived in different categories and depicting it as pieces of the whole, a pie chart is a good option for that. So for example, there's research indicating that happiness is derived from various sources. The idea is there's happiness that we can try and explain, and the happiness pie constitute our level of happiness. The idea is if we could break down what makes us happy, we could understand 100% of what goes into happiness. So the idea is research has indicated that half of what determines your level of happiness is what's called a set point. It's basically your genetic predisposition for being a happy person. So this chart basically depicts that set point takes up the biggest slice of pie in determining what makes you happy versus not. And then it depicts that very small pie slice, the circumstances. This basically communicates that people's circumstances in life and the external factors that are out of our control are essentially pretty minimal in determining our level of happiness. It's really about the things that you intentionally do and your genetic predisposition for happiness that really determines how happy you're going to be. Additionally, if you were trying to depict data about who from psychology doctorate programs ended up in different employment sectors, a pie chart again, 100% of psychology doctorates who graduate makes up 100% of this pie. And then the different slices indicate how much of the pie was dedicated to those different sectors. So you can visualize this pie chart, and it can give a really clear message that the vast majority of psych PhDs end up being employed at a university or for a hospital. Again, the idea is if you're trying to show proportional breakdown for a categorical variable, a pie chart is a great effective way to do that. So one of your potential discussion themes for the week is going to be to think a little bit more about graphics and visualizations. So essentially what you would be doing is just think of some hypothetical variables and draw up some fake data. Just sketch some bar charts, sketch a pie chart, sketch a line chart, whatever you want to do. The idea is thinking about how various hypothetical variables might apply to different graphical depictions. So just draw up some fake data. Fake data is the best data because it actually works the way that you want it to. So go ahead and play around and draw up some graphics. You could use the same variable and just visualize it two different ways, or you can think of two different variables. Again, if you want to do this discussion prompt, just take some notes on what your variables of interest are and draw me some pictures. I would love to see your art. Okay, I'm going to leave it there for this section on visualizations and pick back up with central tendencies.